Welcome back to Differential Equations. In this video, I want to continue our discussion of boundary value problems. This time, we're going to look at this construction called an eigenfunction and see how that relates to when boundary value problems do or do not have unique solutions. You may or may not be familiar with the eigenvalue problem. It is a central idea in the study of linear algebra, and depending on how I've organized my differential equations course this semester, it may or may not have come up previously. But if it has not, that's not a big deal. All I want to clarify right now is that we're going to be talking about eigenvalues, we're going to be talking about eigenfunctions. They are in fact related to the eigenvalue problem of linear algebra, and if you continue further in the study of mathematics, you'll start to see where those links come up. For right now, though, I'm not assuming that you have any previous understanding of the eigenvalue problem, and we'll start everything from scratch. I guess I should start with the word eigenvalue or eigenfunction itself. The prefix eigen, E-I-G-E-N, is a German root that I usually see translated as characteristic. The eigenfunctions of a boundary value problem are characteristic of that boundary value problem. They describe the character of the boundary value problem. And in fact, very specifically, the eigenvalues that are associated with each of those eigenfunctions tell you how you can write the boundary value problem in such a way that it will have a solution. Right. So, let me get my head out of the way and let's dive into some of this. The general statement of the eigenvalue problem for boundary value problems is for a given function, or I'm sorry, for a given real constant lowercase l, identify all real numbers lambda such that the boundary value problem y double prime plus lambda y equals 0, coupled with the boundary condition y of 0 equals y of l equals 0, has non-trivial solutions. And we can play around with the differential equation, we can play around with the boundary conditions, but this general structure of a differential equation that has some parameter lambda in it, boundary conditions at 0 and L, sometimes instead of just looking at things generically, we actually have a number for L, but in this case we don't, and that's actually okay. It is incredibly surprising how little information we need in order to solve this problem. Helps if I put them in the right order. The traditional approach is to break this into three cases. We are looking for a constant lambda, and lambda, if it's a real number, must be exactly one of positive, negative, or 0. So we look at each possibility in turn and see what happens. Lambda equals 0 is almost always the most simple case to figure out. because that always makes the differential equation a lot simpler. In this case, we have y double prime equals 0. Integrating that, we get that y prime is equal to some constant. And integrating that further, we get that y of x is equal to c1x plus c2. Now, applying our boundary conditions, y of 0 is going to just be c1 times 0 plus c2. So we get that c2 is 0. Then y of L is going to be c1 times L plus c2, which is 0, so we don't have to bother writing that down. That also has to be equal to 0. And unfortunately, we can in fact rule out the case that L equals 0. If it were true that L equals 0, then we wouldn't have two boundary conditions, right? We already have y of 0 as one boundary condition. We need a second boundary condition at a separate point. If we only have one boundary condition, obviously we don't have enough information to solve the problem. Unfortunately, that means that L equals 0 is nonsense in setting up the problem, so we can throw that out, and we get that c1 equals 0 as well. And the only solution that we're left with is c1 equals 0, c2 equals 0, which means that y of x is just constantly 0. Case 1 was a failure in this trial. It's not always going to be. Right. For case 2, we're going to assume that, not y, we're going to assume that lambda is less than 0. And in order to get that directly encoded into our differential equation, I'm going to introduce this new parameter, gamma. And the nice thing about a real constant is that no matter what the number is, when you square it, it comes out positive. Any real number squared is positive. Take the opposite of that, and now we have a negative number. So by setting lambda equal to negative gamma squared, we can be assured that what we have is a negative number. With that, in this particular case, we are left with a second order linear homogeneous ordinary differential equation. We can solve that using the method of characteristics. C squared minus gamma squared is equal to 0, which means that C squared is equal to gamma squared, which means that C is equal to plus or minus gamma. Real solutions to the characteristic equation, which means that our solutions to the differential equation are going to be in the form y of x is equal to some c1 times e to the gamma x plus some other constant c2 times e to the minus gamma x. Right, just using the method of characteristics. Now we can plug in our boundary conditions. The first one, y of 0, c1 e to the 0 plus c2 e to the 0. Anything raised to the 0 power is 1. So we really here have c1 times 1, which is just c1, and c2 times 1, which is just c2. Rearranging this, we get that c2 is the negative of c1, and we can plug that in to our original solution here. We have c1 e to the gamma x minus c1 e to the minus gamma x. and might as well factor that out, C1 times e to the gamma x minus e to the negative gamma x. All right. Our other boundary condition, plug in x equals L. And this is the entire reason that I use gamma as my constant in this case. We're going to end up with e to the gamma L minus e to the minus gamma L, and I just find that really fun to write. And this has to be equal to 0. Zero product rule, either C1 is equal to 0 or e to the gamma L is equal to e to the minus gamma L. And that actually only works if gamma L is equal to 0, which means that gamma is equal to 0 or L is equal to 0. If gamma times L is non-zero, then we have a positive exponent here and a negative exponent here, or vice versa, right? We don't know whether they're positive or negative numbers, but if we have one of those exponents positive, the other one negative, then one of those things is going to be bigger than e, the other one is going to be smaller than e, and then we also know that, well, gamma can't be equal to 0, because if gamma was equal to 0, remember lambda is negative gamma squared, and we said that lambda has to be less than 0. We already looked at the case where lambda is equal to 0, we've thrown it out. So if gamma is equal to 0, we have a problem. And we already looked at why L equals 0 is a problem, so we have to throw that out. And we're left with C1 equals to 0, which means that once again, all we have is the trivial solution of y of x is equal to 0 for every value of x. This is starting to look a little bit dire. But luckily, it's not going to stay that way for long, because we have case 3. For case 3, we're going to say that lambda is equal to some other constant alpha squared. If alpha is a real number, positive or negative, you square it, you get a positive number. And this is, again, a way to ensure that when we plug into our differential equation, we have the case that we were talking about. Lambda has to be positive for us to be able to write this. Once again, we will use our method of characteristics. And this time we will get our two complex roots, which means that we have our solutions in the form y of x equals c1 times sine of alpha x plus c2 times cosine of alpha x. Evaluate our first boundary condition, y of 0. This is going to look very familiar. Sine of 0 is 0. Cosine of 0 is 1. And we get that c2 has to be equal to 0. But now when we evaluate at our second condition, y of L is going to be c1 times sine of alpha L. And this has to be equal to 0 because our boundary condition says that y of L is equal to 0. By the zero product rule, that means that either C1 is equal to 0, or sine of alpha L is equal to 0. At this point, we are desperate. If C1 equals 0, we only have the trivial solution, and we don't want the trivial solution. So I'm going to throw that out of hand, and I'm going to force that sine of alpha L is equal to 0. We don't have any control over L. The way I set this up, we're assuming that L is a known value. But alpha, we're assuming, is an unknown value. All we know is it can't be 0. But sine of 0 is equal to 0, but that's not the only value of sine that is equal to 0. Sine of theta is equal to 0. For theta equals 0, pi, 2 pi, and so on. Every integer multiple of pi is a solution to the equation sine of theta equals 0, because sine is periodic. Right? It keeps crossing the x-axis. So this equation, sine of alpha L is equal to 0, is going to be true whenever alpha times L is equal to n pi. We don't want the case when n is equal to 0. That's problematic for reasons that we've already talked about. But if we have n equals 1, 2, 3, 4, and so on, actually we could even pick the negative values of n, but for convenience I'm just going to stick with the positive values. All of these are solutions. And again, we have free reign over what we choose for alpha as long as it is a non-zero constant. So if I just rearrange this equation, I get that alpha is n pi over L. And I can plug that back into my solution here, and we get that y of x is equal to c1 times the sine of n pi over L times x. Again, for n being some of our constants. Because this function has a couple of variables in it, right? Again, L is taken to be a parameter that is known to us. I don't know what it is. I'm trying to solve this in general, but that's given to us in the start of the problem. There's not much we can do with it. C1 we actually have complete control over. For convenience's sake, I'm going to pick C1 equals 1 just to make life a little bit easier. But to indicate that we have a free reign of this n as well, it's traditional that we are going to call this solution y sub n of x. And sometimes you'll see the x show up in the numerator instead of being in front of the fraction. Either one is acceptable. It's a stylistic choice depending on your discipline and where you are coming across this eigenvalue problem. Right? But these are the eigenfunctions of the boundary value problem that we started off with. This is what our general solution looks like. We don't know which value of n makes the most sense. We need more information about the problem in order to actually answer that question. We will look in the future at how to find more information about that. But before we wrap up this problem, I also want to point out that the parameter that was actually in the equation was not n or alpha, it was lambda. Remember that lambda was alpha squared, so that's n pi over L squared, which is n squared pi squared over L squared. These are called the corresponding eigenvalues for this boundary value problem. And again, remember that prefix eigen means characteristic. So the characteristics of this particular boundary value problem are that the solutions occur when the eigenvalue, when the lambda in the equation is n squared pi squared over L squared, and then the solutions take the form of sine of n pi x over L. I'm going to wrap up, as I always do, with one for you to try. I do want to caveat that this is probably the most involved problem for you to try after a video in the entire course, but we've gotten to the point where there's really not any simpler problems for me to give you. So, I want you to look at another boundary value problem. The differential equation itself should look very familiar to you. Y double prime plus lambda y equals 0. This time I'm giving you a slightly different set of boundary conditions. Y prime of 0 is equal to y prime of L is equal to 0. So instead of having information about the function, we have information about its first derivative. That changes things a lot less than you would think it would. So go through, follow the process I used for solving the boundary value problem in this video, and see if you can solve that one. I guess before I wrap up, I should also mention, what does this boundary value problem represent? Well, one of the places that I like to think about this is in terms of a flow rate. So if you have some sort of a tube, and you have control over the rate at which your fluid enters the tube, and you have control over the rate at which the fluid exits the tube, and you want to know what is happening inside the tube. That's the kind of thing that you can answer using this sort of boundary condition. Right? This is not an applied physics course, this is a mathematics course, so I'm not going to worry that much about the details, but that's the kind of thing that you might want to keep in mind as you're trying to solve this. Right? So with that, take a couple of minutes, see what you can do with this one, and I'll see you in the next video.